I got a few recommendations that I kept here. You don't want to have too many tasks in the system because it requires more RAM space. You don't want to have too few tasks in your application because it defeats the purpose of having an RTOS. If you got one task, it makes no sense. If you get two, it's kind of questionable whether you need an RTOS or not. So anyway, so there's a number of tasks, maybe 8 or 10 or something like that makes sense to use an RTOS with, or maybe 2 is good enough. Don't know. You want to keep your ISR short, clear the interrupt, signal a task, let the task do the work. In the case of a non-kernel aware ISR, you only use those when absolutely necessary and when they need to be super short. You don't want to hog the CPU when a non-kernel aware ISR occurs. You want to set task priorities at design time, avoid changing priorities at runtime. Let the kernel do that in the case of the mutex because it's a built-in mechanism, that's fine. Use mutexes instead of semaphore for resource sharing. Then talk about round-robin scheduling. It's a method to actually give equal priority tasks a chance to run. Basically, the RTOS will run each task of the same priority for a certain amount of time before relinquishing the CPU to another task. So I've done a lot of embedded systems, a lot of system with motor control and stuff, and never really needed to use round-robin scheduling for those cases, but it could be useful. The problem with that is that, well, it could potentially starve low-priority tasks. Keep the number of priorities low. That's more of an efficiency thing than anything else. By keeping the number of priorities low, below 32, for example, in the case of MicroCOS 3, it makes scheduling extremely fast through a special instruction called the count leading 0 instruction on the Cortex. Anyway, so other processors have that instruction as well. So RTOS APIs consume CPU cycle. Be wary of this. Don't enable the FPU if you don't need. If you don't need to do floating point, there's no point of enabling that and thus saving a whole bunch of registers that are saved and restored from the stack. And I recommend creating graphical objects or models of your application. So using some of the little pictures that I use makes understanding how an application works. General thing about RTOS and in fact embedded systems, avoid using malloc and free. If you don't delete RTOS objects at runtime, then you could use malloc and free to create your RTOS object as long as you don't use free. The task could own resources that others need, so deleting a kernel object could be kind of devastating for the operation of your system. You want to avoid excessive stack usage, so don't allocate large arrays on the task stack unless that's something you absolutely have to have. Some linkers give you an idea of the stack usage per function. So for example, the IR compiler gives you a table that says this function requires so much stack space that because it calls all these other functions, quite useful to determine how much stack space you need for each of your tasks. You want to keep the data in scope, especially when using message queues by reference. So you don't want to produce data and then somebody else tampers with that data until it's actually consumed by its recipient. So you want to make sure the recipient is the one that actually discards the data structure that you've allocated when you sent the message to a task. Use data queues if you're sending small amounts of data. That's always a recommended thing to do. So again, using the MPU, highly recommend that any application, from now on, if you have an MPU, memory protection unit on your processor, I highly recommend to use it. It makes your design a little bit more complicated, in some cases a lot more complicated. And the complexity is not really the use of the MPU. The complexity is into setting up these memory areas and working with linker scripts that actually specifies how memory is actually laid out. There's a feature called the execute never bit. So whenever you're using the MPU, I would highly recommend you wrap the RAM locations that you wrap, you set them with execute never, meaning that code could not execute out of RAM unless you need to, unless you're updating your firmware in the field or something, you may need to turn off that bit when that happens. Each process should limit access to its own peripherals. Reduce the inter-process communication. Yeah, you could use shared memory, but there are other ways you could actually share data. I didn't get into those details. You want to create name sections for your RAM. So when you're writing your system, if you're going to be using an MPU, start naming the sections of your RAM by giving them names that would be associated with these processes. It makes it a lot easier to create those linker scripts I mentioned. Don't use global heaps. You cannot protect a global heap using the MPU. Don't pass data from one task to another task as much as possible, because if you're protecting one task stack and you're passing data from one task stack to the other, then you would get an MPU violation, although you'll find out soon enough when that happens. So all kernel objects should be allocated in kernel space. Didn't really mention anything about that, but that's something I could do in a separate talk. But yeah, just make sure that kernel objects are in a specific memory space reserved just for the kernel to access.